Yeah, hi everyone. My name is Apoorve, and I'm a staff research scientist at IBM Research. And with me, we have.
Tzu-Mainn Chen, I'm a principal software engineer at Mohan.
So you heard Mohan briefly talk about ESI, and we are going to overview what we did in the past, what's the present, and what's the future of ESI. So, I mean, in the 5-minute presentation we are going to do, if you want to sleep, okay, just focus on this one slide. So, what is ESI? ESI stands for Elastic Secure Infrastructure, a system architecture to enable rapid and secure multiplexing in a data center. And to achieve this, what we did at MOC, and this is like just not me, it's like a lot of my peer PhD students, a lot of engineers. Some work was also done by Ran and Peter and other professors, but that's a separate discussion. So we built a framework, we proposed a set of microservices and how they should interact with each other in order to achieve this. So yeah, now you can see. So why we need this? Why was ESI conceived in the first place? So there existed virtualization layer, which essentially provided elasticity, improved efficiency of your aggregate data center resources, but still there are a lot of use cases that wanted bare metal access. As Peter mentioned, as an OS researcher, he wants access to the hardware, right? There are organizations such as financial institutions, Tzu-Mainn Chen here, who want direct bare metal access. They don't want any virtualization layer. USRF was another use case, right? So what in a traditional data center, what these organizations do, they set up these bare metal silos and essentially set up a lot of these silos in the data center running specific frameworks to control specific workloads. For example, people are aware of Slurm, OpenStack, OpenShift these days, right? But one thing that they miss is they do not try to move infrastructure between these silos due to various either security reasons or operational reasons. And because of this siloing, what happens is your aggregate efficiency of your entire data center reduces. So let's see example. So what we did was, as a part of our journey, we analyzed various traces from production clusters. For example, here on the bottom, you see 4 different plots. I know it's hard to read, but one was from Microsoft Azure, where we looked into what are their aggregate usage pattern or aggregate allocation pattern for their virtualized instances. Similarly, we looked into some data from another time-sensitive workload from 2 Sigma, where we saw like there are huge gaps in what is the actual capacity versus what's the aggregate or allocation patterns. Then we looked into some batch-style clusters, right? Where we have this one from the Open Science Grid project, where you see burst of workloads coming in, and these are all single node jobs. Another one is from the Mustang supercomputer cluster, where you have long queues. So what we thought was, what if we were like these clusters were actually co-located in the NGHPCC like data center. So if you do that, your aggregate capacity basically increases to this dotted black line you're seeing here. Your aggregate allocation is this magenta line, and you have a batch queue that you can potentially serve very fast with this excess capacity. However, if you want to do that, there are certain constraints that you need to keep in mind. For example, 2 Sigma might be reserving these resources for failure. But if you aggregate them, you get more resources from other co-located clusters to manage those kind of failures. But in order to leverage extra resources from co-located clusters, you need to have elasticity at the bare metal layer. So we identified 3 key aspects of how to achieve secure bare metal multiplexing or secure bare metal elasticity in such a co-located environment. And the first important requirement was dynamic isolation. I'll briefly overview about what this layer is and what we did to achieve it. Then we have had something called for software stack setup and resetup, because we need to move infrastructure really fast across these different clusters. And then if you're operating in a multi-tenant environment where co-located parties do not trust each other, you need to ensure that when you are moving this infrastructure, and if the infrastructure was compromised by a previous entity, you should be able to figure out before you hand it out to the next entity. So briefly going over this, so for this entire ESI, Elastic Secure Infrastructure, we proposed three primary microservices. First was the network isolation service, that is a very minimal layer, like an exokernel-like layer that manages your networking infrastructure to ensure isolation between different clusters. The next layer we built was for bare metal provisioning, and this is a diskless provisioning approach where we disaggregated the state of the machine to a backend, and we expose the boot images from an RBD data stock device and booted the physical servers out of it. And finally, we added trusted boot and remote attestation using keyline on top of it. And this entire architecture we refer as ESI, which enables rapid and secure bare metal multiplexing. So we evaluated our system, our prototype systems that we developed, and there are a lot of results. I'm not going to go over all of them, but these are some of the highlights we can talk offline. So this was what we did in the past while I was a graduate student here. So Ming will talk about what's currently happening, how they are implementing ESI in real world using OpenStack.
Hey, so as Cor said, I'm Tzu-Mainn Chen. I'm a principal software engineer at Red Hat. And for the past couple of years, I've been working on ESI alongside a talented team of software engineers. And I'm just going to give a really quick view into our development efforts at ESI. So first, there's two quick actual definitions of ESI. First one, ESI is just a multi-tenant bare metal cloud where users can come in, use a couple of nodes, hook them up to a private network, create your own isolated bare metal cluster. It's also a place where multiple organizations can pull their hardware together into one cloud. And under such a scenario, if you plan the hardware, you're by default, you're the only one that can see your nodes. You can use it however you want, and other people won't even be able to know that the nodes exist. You can choose to share those nodes if you want, but that's completely up to you. The second view of ESI is really right now just OpenStack. And you can think of it as a specific configuration of key OpenStack services, namely Ironic and Neutron. When we started working on ESI and discovered that a couple of features needed in OpenStack that were missing, we worked to implement them upstream of OpenStack. And what that means is that if you have an OpenStack installation version Wallaby or more recent, then in a certain optimistic sense, you kind of already have ESI installed, right? But yeah, that's pretty great. Now, we do have a little bit of code that's written on top of the OpenStack stack, namely ESI, which is a very, very simple leasing service. And all that does is it keeps track of leases and cause the OpenStack Ironic APIs to assign and unassign nodes to particular users. And you don't really need it. You can do the same thing with the OpenStack Ironic API and a spreadsheet. But ESI just automates a bunch of things and makes reporting a whole lot easier. So for the past year or so, we've been focused on usability testing. And the first question there is, do the OpenStack APIs have the functionality we need? So with nodes, can we configure and manipulate nodes? Can we control the node's power settings? Can we have a node boot from a volume or boot from an image or boot from disk? So far the answer has always been yes. The OpenStack ironic APIs are pretty comprehensive. The other thing we looked at is ML2 networking, and here we're asking, can a user create a private network with its own VLAN, and then use OpenStack neutron commands to configure the switch so that the node is on a VLAN? Again, the answer is yes, that works. We did have that support for a couple of switch types, but I got that really simple because I didn't have to do it. But if you talk to Naveed, who did do the work, I think he would tell you that it's actually pretty straightforward. One thing we did discover, though, is that a lot of the workflows we wanted to do took a lot of OpenStack commands. So, for example, attaching a node to a network, you need 5 or 6 OpenStack commands in order to do that. So what we did is we created a Python ESI client, which is an OpenStack CLI extension, and all it does is it calls existing OpenStack APIs and chains them together, so you can take those long workflows and use a single command. So attaching a node to a network, one command. Viewing the network configuration of all nodes, using the base OpenStack CLI, you need 5 or 6, again, CLI commands per node. So yeah, 20 nodes, that's 100 commands. Using a Python ESI client, you just need to run one, and you get the output in nicely. So once we were done with all that, our next question was, does ESI support practical architectures? So we started with a very simple test. We installed a keyline on the node, created a private attestation network, leased a couple of nodes on ESI, and then just attach those nodes to the private attestation network and verify the keyline could attest those nodes. And yeah, that all worked. It was good. Our next test was a little more complicated. We installed an OpenShift cluster on ESI nodes, and using the OpenShift assistant installer. And again, the answer turned out to be a lot simpler than we thought it would be. All you have to do is lease a couple of nodes on ESI, configure the networking, configure the nodes so that they pull down images from the system installer, and you're basically done. The system installer will take care of the rest, and at the end of the day, you'll have an OpenShift cluster. So that kind of speaks to how we really want people to use ESI, which is kind of as little as possible. You're going to use ESI to lease nodes, do some network configuration, configure the nodes a little bit, and then you'll use your own tools to do whatever it is that you want. You don't care. So recently, we deployed ESI to MOC. It's a HA OpenStack installation. There's 30 nodes on 3 switches, and we're constantly adding more. Currently working to onboard researchers to gather feedback, mostly a lot of documentation. And if you're interested in trying it out, you should just let us know, and we'd be happy to hook you up. So, key takeaways. Number 1, ESI works. MOC ESI is available for testing now. You can deploy your own ESI installation just by deploying OpenStack. And we welcome any feedback and contributions that you might have. And if you'd like to talk some more, we have a Birds of a Feather session at 1:15 p.m. in room 315. We have a pretty nice website. Yes, today, yes, definitely today. We have a nice website, and you can find our team on IRC in the OFTC network, in the MOC channel. Thank you.